Hello everybody. I'm trying to show you how you can find in this video the what we call the principal stresses, or also known as the maximum stresses. So principal, note that principal is spelled like that, CIPAL, which you'll see they are the maximum stresses, and we're going to use the notation sigma 1 and sigma 2. One is minimum, one is maximum. Both could be in tension, positive, both could be in compression, negative. But one is larger than the other. Okay, so this is basically what I'm trying to show you this video is because if you've seen the PowerPoint presentation that I put on Blackboard and the narration didn't make sense, hopefully this will clear some things up, so basically, just to summarize our transformation equations, if we have a state of stress of a point on a structure as a plane stress format, so a two-dimensional stress element that's shown here, right? So we have sigma x, sigma y, and tau xy, right? So basically, remember, this was a three-dimensional stress element, which we, change it to a two-dimensional one, right? All right, and then we said that if we look at a different plane, so if you look at some other plane, which measured by this angle theta, so basically, if our initial axis is xy, we go to x prime and y prime plane, right? What would happen to the stresses? So what would be sigma x prime, sigma y prime, and tau x prime, y prime? So here we have the equations, and it's done based on a derivation, simple derivation. So this is the equation for sigma x prime. Notice that the angles, instead of the theta here in the equations, for convenience of what you'll see later on in terms of graphical approach, more circle, they're changed to 2 theta. Okay, now notice that the only difference between sigma y prime and sigma x prime is that the positive here has changed to negative, and the same thing here, positive has changed to negative, but this average kind of a stress remains the same. Now, the reason for that I've shown you before, because the difference between this plane, x prime plane, and the y prime plane is 90 degrees. So basically, if you add to theta, the 90 degrees, you go to the sigma y prime plane. And when you double that, it becomes 2 theta plus 180, and as a result, the cosine of those angles becomes cosine and sine of those angles becomes negative. All right, one interesting thing that I mentioned before is that if you add sigma x to sigma y, that should be the same regardless of any, for any angle or for whatever plane, it's going to be the same as sigma x prime plus sigma y prime. So in other words, the sum of two normal stresses on two perpendicular planes is going to be what we call an invariant, a constant. Okay? So now, our objective is to find principal stresses. What are the principal stresses? Principal stresses are maximum normal stresses, which eventually we're going to call them sigma 1 and sigma 2. How do we do that? So we start with this guy, sigma x prime. You guys know, anytime you're trying to find maximum of something, what do you have to do? You have to take the derivative of that with respect to the variable angle theta and set it equal to 0. So if you do that, the derivative, the first term is just a constant, is going to be 0. The second term, they have sigma x minus sigma y over 2. The derivative of cosine 2 theta becomes minus 2 sine 2 theta, right? And the derivative of sine 2 theta becomes 2 cosine 2 theta. If you rearrange the equation, in other words, if you, for example, divide by cosine 2 theta, both of these, you notice that this cancels and this becomes tangent 2 theta. So it becomes tau xy divided by sigma x minus sigma y over 2. Let me go to the next page. And I have rewritten this equation for the tangent, right? And this is not any angle. It's an important angle. We call it principal angle, because at that angle, you will get the maximum. So you guys also remember that once you find that angle or variable at which whatever you're trying to maximize becomes maximum, what do you have to do? You have to go back to the equation, this equation here, and then plug in what? Plug in the cosine 2 theta and sine 2 theta to find the maximum of this guy, which now becomes sigma 1 actually. So the problem is that we have tangent of the angle, but we need sine 2 theta and cosine 2 theta to plug in. But that there is a remedy for that. So if we say tangent is, look at this triangle and say tangent is what? Opposite over adjacent. And then find the hypotenuse of this triangle, which I called it R. And the reason I call it R because I don't want to carry that all the time. So R actually happens to be the radius of that Mohr circle, the graphical approach that we're going to talk about later on. Okay, so take this sine 2 theta, which now is what? Tau xy opposite over R, right? And cosine 2 theta, which is now adjacent over hypotenuse R. And go back and put that sine 2 theta here and cosine 2 theta here, right? And you're all set. If you clean that up, and it's very easy, guys, you could show that on your just write it on a piece of paper and show that the outcome becomes this. And notice this is again R here, this radical term. So actually basically sigma 1 and sigma 2 becomes what we call an average stress plus and minus R. And later on, as I said, you'll see that R is called the radius of the Mohr circle. Anyways, so now to show you what's going on is that if this was the initial stress element, right, we basically, if you find that theta, by the way, I did call this angle. Now, once you find this angle, I'm going to call it theta 1 now. Theta 1 here, sorry. And then the angle that will give us the other sigma 2, and remember sigma 1 goes with the positive here and sigma 2 goes with the negative here. The other angle is always 90 degrees, positive or negative from that, and hopefully you'll see that here in this picture. Okay, so once you find this angle theta 1, right, just if you get positive, just look at a plane that is counterclockwise, and by the way, this is also theta 1 as you can see here. Now, on this plane, you get sigma 1 and you get sigma 2 on the plane that is 90 degrees from that. You see that? So the plane between sigma 1 and sigma 2 is 90 degrees. So you theta 1 plus 90 degrees, right? Will give you theta 2. Notice that the shear stress here on this plane or on this plane, right, is going to be 0. So shear stress, if you go ahead and try to find tau x prime y prime based on the transformation equation and based on the sine 2 theta and cosine 2 theta, you get 0. So the important thing is that the shear stress on the principal plane is equal to 0. And that's always a rule. Also notice that that invariant that we were talking about, sigma x plus sigma y, equals sigma x prime plus sigma y prime, also applies here. It must be equal to sigma 1 plus sigma 2. And this is a good way to check your answer, actually. So hopefully I'll come back with an example of this. Maybe I use the same problem that I showed you for the transformation example. And we'll keep using the same problem so you see different version of that. And actually, before I do that, I'm going to come back and show you how we can actually maximize the shear stress, doing exactly what we did here in this video. As always, thanks for watching and listening. Stay safe and healthy.